Hello, welcome to today's webinar on structure analysis of bridges to Eurocodes. In the next 45 minutes to 1 hour, we'll be going through the different uh, key points that we need to make note of while generating our structure analysis model and setting it up for the next stage, which is design as per Eurocodes. Okay, so in this particular webinar, we'll be looking at first of all how to set up the model for structure analysis. Now we won't be going through the entire modeling process, but we will just focus on the few things that we tend to miss out, or maybe important points that are required if we keep in mind if we are checking the bridge as per Eurocodes. Okay. And the next part of this webinar will be going through the different kinds of loads and actions that we apply on the bridge, which are listed over here. So let's look at first of all how to set up a model for structure analysis. Now there are different kinds of models that we generate based on the results that we want in our design. The first one being a simple line model. Okay, now line model is very commonly used for bridges like concrete box girder viaducts, which are post tension bridges, for example, and then footbridges which have a very narrow slender deck. This is on the right hand side. You can see the post tension bridge, box girder bridge, and then it's also used very useful for cases like you have a multi girder bridge, such as shown here in the below right side, where you can take out one of the middle girders and analyze them separately with loads put on them uniformly, and then just have a quick check on the results and dimensions are correct or not. For wide deck bridges, normally we use a grillage model or a plate model, but even here we may use a line model, such as the scenario which is mentioned here. You have a very wide deck with a spine beam at the center. These kind of structures, if we want to check for stability, just have a look at the bearing reactions and just a global stability check. We can model a simple line beam and put the wide deck or other components as a load on it. Okay, and also sometimes a line model can be used as a temporary model just to use the automated design checks in the software. So let me just go through quickly a few of the models that we can look at here. Right, so I'm just opening one of the models in Midas Civil. Okay, so first one that I'm going to open is simple concrete bridge. Okay, so here we are. It's a plate model. The deck is modeled as a plate, and the central spine beam is modeled as a beam elements. Okay, now this structure, as you can see, is a little complex, but if we want to just check the bearing stability, we can convert this into a line model. Okay, and just model the central spine beam. So we have a line model which looks like this. Okay, so that's how the line model looks like, and here if you see, we've got the bearings at the correct location. So it's very important, if you're doing a stability check using line model, is the location of the nodes, the bearing points should be correct, because here we are not trying to simulate the exact stiffness of the model, but rather we are trying to simulate the load distribution correctly. Okay, so I'll just display the elastic links to show you how they are connected. So we put a node here and connected it rigidly with an elastic link. So I'll just display the rigid links also. Okay, so these are the rigid links to these points, and then we have dropped some further rigid links, and these small ones are the bearing points. Okay, so what we can get out of this particular model is the reactions at these three bearings, and then we can see for which particular combination it is critical, or whether it is stable or not. Okay, and the second case can be, as I said, can be a simple design checks. We may be having a very complex plate models, such as we may be having a composite plate girder bridge, and we have modeled the deck as plate elements. Now when we use plate elements for our analysis, the automated design checks that are there in the software, they don't tend to work directly. Okay, so if we want to use those automated design checks to save our time, what we do is we prepare a simple line model. This is like, as you can see, it's a composite beam section. It's a simple line model which has a fixed support at the other end. Okay, so for design of composite sections, please refer to other videos from Midas on how to design composite sections, and also we have subsequent webinar on this topic. But here I'm just trying to show what we can use a line model for. So what we do is we extract the plate model results in the form of shear force, bending moment, etc. We apply that as a point load at one end of this cantilever. So I'll just show you how that has been done. So I've applied a moment here. The units are in, let's say, kilonewton meter now. Okay, so moments are applied, and so is the shear force. Okay, and we've developed just simple construction stages before composite and after composite section, and using this particular model, the software can now give automated design check results, which was earlier not possible directly when you used a plate model. So earlier we had to use Excel sheets to design the composite sections or any other type of section, which can tend to be time consuming and may lead to mistakes, human errors. Okay, so that's where typically the line models are used. Now coming to the grillage models, grillage models are very common for multi-girder type of bridges where you have a very wide deck, and you need to look at the local results as well, like transverse bending and as well as longitudinal bending. We go for multi-girder bridges for grillage models. Now, why not plate models every time? Because again, grillage models being it's just a line type of modeling, we can use the checking features or extract the forces very easily from the software. Okay, now this can be used for any type of skewed, wide decks and curved type of decks. Okay, but the important thing is that in order to make sure the deck is modeled properly, the shear lag effects have to be considered very accurately. This is the only drawback with the grillage model, is that you have to do further calculations to make sure the stiffness of your longitudinal and transverse members are correctly considered and that shear lag effect is being taken into account. Okay, which means you have to make sure effective width is very properly calculated for each span, center and support of the span, etc. Okay, now I'll take up some few examples just to elaborate on these points that I mentioned. Okay, so just opening up Grillage model. Okay, okay, so we have a grillage model here of a composite steel girder bridge. This has a concrete slab and steel box girder type of section. Just to show you how it looks like, I'll just extract a part of the model. So that's how the section looks like. You have a composite box girder and it's a curved type of profile. Now I'll just focus on some of the important points here which were used for the modeling purpose. Okay. Now in such kind of bridges, multi-gutter bridges, while you are generating the grillage model, uh, obviously it's very important that you have proper connectivity between the longitudinal and transverse members. Plus it's very important to make sure we have all the splice zones as well marked on the grillage model. So such as if you see these nodes here, from analysis point of view, they don't have a real significance in this model, but they have been put here because we need the results of shear forces, bending moments at the splice locations where the two steel girders are spliced. So we need to put some extra nodes there. Okay. Then another thing which is important is the effective width, as I mentioned, the shear lag effects that need to be considered properly. Now, for the shear lag effects, we have certain features in the Midas software as well, which can calculate the effective width automatically. So in the structure you have composite bridge effective width, so it will calculate the effective width if you put in the shear connector distance, for instance, and you have to mark the span that you are going to consider. So it will find out whether it's an intermediate support or it's an end support. So in the composite bridge span information, we need to add the span information for this bridge, and it will calculate the effective width for the support location and the mid-span location. So that will ensure that we have got the stresses calculated correctly in our model, so that when you're designing it, we are getting the correct the stress value that is being used in the design checks. Okay. Now another thing is that for composite steel bridges, in the grillage model itself, we should have the correct location of the bracings, the lateral plan bracing, and as well as the vertical K bracings. Okay. Then for transverse elements, it is important that for transverse elements we decrease the torsional stiffness of those transverse elements, because we want to be little conservative while designing the longitudinal girders. So what we do is, let's say if we have a transverse element over here, we reduce the torsional stiffness. So many times we model the transverse elements not as a database or a default section, but rather as a user defined section with our own properties input here. Okay, so transverse elements is basically represent the transverse bending of the deck. So we just modify the IXX or the torsional stiffness value. In some cases we put it to 0, and in some people also prefer to keep the torsional stiffness as 50% of the original one. Okay. Of course, the width of the rectangular section that we consider as a transverse beam is generally kept equal to the center to center spacing of the transverse beams. Okay. Similarly, if we are designing the longitudinal if you're designing the transverse rebars in a deck using a simple beam design technique in the software, we would like to put some conservatism on the bending moments of the transverse elements. So in order to do that, we then reduce the torsional stiffness of the longitudinal girders as well. Okay, so we do that more often for steel plate girder bridges, because they are not really designed to carry torsion. Okay, so we keep the torsional stiffness is 0 in those cases. Just to show you where we do that, in a composite steel bridge, we have a composite section for construction stage, and we just put the stiffness scale factor for the deck as 0 over here. Okay, it can be 0, it can be 50% based on the engineer's judgment. Okay, all right. So these are some key points here. Now many times there are some modeling issues when it comes to curved bridges. Okay, so this is a curved bridge example. So I'm just going to show you what technique you can use in your Midas software to generate a curved bridge easily with, I mean, with the grillage of transverse and longitudinal elements. Okay, so we have got a new project open here. Okay, so for a curved bridge, first of all, in Excel or any other spreadsheet, we need to calculate the angle traversed by each transverse element. Okay, so what I mean to say is each bay of a grillage will be separated with each other by a certain angle with respect to the center of the of that curve. Okay, so that angle needs to be measured and needs to be calculated in Excel or on any other format. Okay, and then what we have is let's say I create a node at origin. Okay, there's supposed to be the center point of the bridge, and I then mark the center of this the curve. So just extrude sorry. Right, so let's say the radius is 200 meters. Okay, and I marks few other points to just to denote the actual position of the girders, actual origin of the girder. So it has got four sets of girders in a curve. So I'm going to just copy those points in. Okay, so just copy this. So all the girders are spaced at 3-meter intervals. Okay, so I've got the girder locations at the initial point, and now I'm going to just copy or create elements out of these girders on a curve. Okay, so I can use extrude elements and use the rotate function over here, unequal angles. So this is where you put in the exact angles of the grillage elements, so which are going to be rotated about this point. Okay, so let's say I have got 10 bays at maybe 2 degrees each, and then I've got 5 other bays at maybe minus 2.5 degrees, something like this. Okay, and then the rotation point is this one, which is the center, and I click apply. So I've got the girders generated. Now same way I can generate the transverse elements. I just need to create the first one. So I've got the first one generated, and I'm going to copy these transverse elements. Okay, now you can put some properties in initially, because if it's curved, then putting properties later on might be a little difficult to select and then assign. So I prefer normally to generate the properties beforehand. Okay, right, so same thing I'm going to do here. I'm going to translate it, I'm going to rotate these transverse elements. Okay, okay, and so after generating this, I can just simply delete this, don't need this one, and you can see the grillage is generated. For skewed bridges, all you need to do is just move the coordinate points a little bit and then further subdivide the elements in between, and you have got the bridge generated quickly. Okay, so this ensures that you have got a proper spacing of the transverse elements, the distance. You can assign the properties correctly to this transverse element based on the spacings here. Okay, and and it's easy to extract results as well, because you know at what angle you can just pull the member out from here. Numbering is also uniform. So going back to the presentation. Okay, so let's look at now the third type of model that we use for our design is a plate model. Okay, now this is used for accurate modeling and detailed design. Okay, the benefit is that we don't need to worry about any kind of shear lag effects here, because they are automatically considered as the deck is being modeled as plate. Okay, so both longitudinal and transverse properties are put in correctly. But however, the design checks are not automated. You have to extract results from the software, because plates mostly give you the stresses and local forces. So you have to convert those into global forces. Of course, you can use the software for that, but then again you have to put that force in some Excel sheet, or maybe in another model of yours, maybe a line model as I mentioned before, to design it. This is very commonly used for highly curved decks, where it's difficult to uh, uh, approximate the grillage properties, and in U-frame type of bridges, where you can have lateral torsion buckling, and ladder deck type of bridges, where effective weight calculation of the longitudinal main girders can be tricky, because you don't only have to calculate the effective weights in the longitudinal direction, but also in the transverse direction. Okay, so I'll just take few examples here, just to show you different things that we need to make sure the plate model is correct. Okay, okay, so here we have a U-frame type of structure. You have the eye girders on the both sides, and then the concrete deck has been modeled as plate elements. The transverse girders, cross girders, are modeled as beam elements. So just to show you by highlighting them, these are the transverse girders. These type of models are mostly used for local bending effects, and to check the where the beam theory not necessarily applies. Okay, so in order to check the U-frame action, it is very important to model the structure as plate elements, because of the reason that you can actually see the buckled shape of the top flange. Okay, so I'm just going to give you an example here, like one of the buckling modes which looks like this. Okay, so that's the kind of results that you can get from this model. Plus, even live load wise, it gives a very good distribution of live loads. We'll focus on that when we move on to the second part of the webinar, which is the applying actions. Okay, then you have certain cases where you want to model only the deck as plate elements, and keep all the girders as beam elements only, because you don't want to calculate the effective width. So this is very common technique for curved bridges and skewed type of bridges. So I'll just open up another model here, which is similar to the curved looked at. Right, so here we have the same bridge, uh, again composite box girder, steel box girder bridge. Let's look at the deck only right now. So I'm just going to highlight the deck. Okay, right. So that's the plate elements that you're seeing on top of the deck. Here, you will see that there is a clear distinction. There is something missing over here at the in the middle. That's because the 15% of the span on either sides of the internal support um, will have the slab as cracked because of hog and bending moments. So that's why the plate elements that are over in this region have been assigned with different properties, that is longitudinally cracked, and that can be defined using orthotropic properties for the plate. So you can define in materials, you can use, instead of isotropic, you can use orthotropic material property, the user defined section, and define different properties in x and y direction. Okay, now how to extract results from this particular model? For that, there are few features used for calculating resultant forces. One of them is in the modeling unit itself. So we've got something called section for resultant forces, where you just select, suppose you want to get a cutout of this section, so you select all the elements over here, okay, on the deck, and then click add, give a name to it, and so it calculates the resultant at this location. Of course, I selected the entire deck. You only need to select the ones that correspond to one girder and the effective width of the slab for that girder for calculating the resultant forces. Okay. Right. So now we move on to this next part, which is the Eurocode actions. So as per Eurocode, we have the actions categorized into permanent, variable, accidental, and seismic. Okay, so in this webinar we won't be focusing on the seismic action, but we'll look at the other aspects of the actions. So let's go to the first one, which is permanent actions. So for permanent actions, self weight corresponds to the basic structure permanent action. Then we have weight of bridge furniture, which is like parapets, surfacing, etc. Ballast in case of railway bridges. Okay. And sometimes the weight of the earth that is acting as an overburden on culverts. Okay. The way we model these are as self weight, we use the auto self weight calculator, also known as body forces in structure analysis software. So in the auto self weight calculator, we just specify the direction. So say for example, if I needed to apply permanent loads on this model, I'll have to just use a self weight option and then just put the direction in as -1 and apply it. Okay. Similarly, if I want to put in some other loads like parapet loads, so in order to put parapet loads, since Midas doesn't give you the option for putting the loads as a patch load on a grillage. Okay, so you don't really you can't really apply a line load if you don't have a member sitting underneath it. Okay, so for that purpose, I need to make sure that in your grillage model you have those lines created. So for example, in this grillage model, I have these external lines created which represent the parapet loading. Okay, so in these lines have been assigned with very minute properties, maybe 1 millimeter or something, just for the purpose of loading, and we apply a beam load on it, which can be accessed from loads and element beam loads. Okay, so put the value of the load in and then apply it. But if you're using a plate deck, then you don't need to really have all these internal elements, line elements, extra line elements, because in plate elements we can actually apply these loads as a patch load. Okay, so how we do that is we define the plane load type, either point, line, or area. We put the, say suppose it's a line load, we put the actual coordinate of the line load, um, x1 y1 x2 y2, and after defining the plane load, we assign the plane loads on the loading plane. Okay, so since we have defined the entire length on which the line load will act, we need to define the elements on which it will be distributed. So we select the plate elements and just click apply, and it will automatically project those loads on the plate elements below that, below the plane load we have assigned. Okay, so in case of grillage models, in summary, we need to be careful that we have got the extra lines for assigning our SIDL and surfacing loads. And in case of plate elements, we can either apply it as a pressure loads if we have divided the plates at such locations, or we can use plane loads. As mentioned here, we can define a patch load and assign them. And now plane loads are good, but it's always recommended that you actually divide the plate elements and beam elements wherever you have a load, because it just makes it easy to extract the results and maybe later on change the value of the loads, maybe move the nodes a little bit inner or outer direction to adjust the actual position of the dead load. Okay, now moving on to this next part, which is wind loads. Okay, now wind loads in Eurocode, defined in Eurocode 1 part 1.4. There are three types of wind loads that we defined for our analysis. One is the transverse wind load, which basically is calculated based on the drag coefficient, and drag coefficient depends on the shape of the cross section. So if it's a box, or if it's a circular type of section, etc. For the superstructure, there is an equivalent formula that is given in Eurocodes for calculating the transverse wind loads, which uses the basic wind velocity and global wind factor. Global wind factor again is given in a table in the same code. It is then multiplied with the exposed area of the bridge, which is in the case of an unloaded structure, it will be the just the overall depth of the superstructure. In case of the loaded structure where the live load is leading, then the wind load is applied as an accompanying action, including the height of the live load plus the overall depth over here. So that's how the exposed area is calculated. Now once the transverse loading has been done, in certain cases we may have longitudinal forces as well. So for longitudinal forces, we generally take 25% or 50% of the transverse direction load and apply it as a UDL in the longitudinal direction. So just to give you an idea about how the wind forces are applied, in a curved bridge we can choose to apply it in the direction perpendicular to each element. Okay, although wind will not flow in these many directions simultaneously, it will flow in one particular direction, but to be more conservative we can use this kind of approach and then design it. So what we do is we select an element, in a whole line of elements. So let's say I select this line of elements over here. Now in this particular structure we have 4 girders, so we can choose to split up the wind forces in 4 girders equally, but I'm just selecting one end and then to show you how it is being distributed. So just select element beam loads and maybe the category as wind transverse, and the direction is local Y. Okay, so local Y direction. Another thing that we need to assure in a grillage model or any plate model is that the local axes are aligned properly, otherwise we'll end up with results which make no sense. Okay, so we put the load value in, which is calculated from the equation I just mentioned in the slide, and then that's it. The wind loads are applied. just to show you just a display of that. Okay, so I'd applied it previously in this direction, in this particular line element, so that's how it is shown. And for vertical wind loads, lift coefficient is used. Again, the lift coefficient is given in the same code for different shapes, aspect ratio. The exposed area will be different because it's a vertical load. The depth of the section will not be used, rather the width of the section will be used for calculating the exposed area. Okay, after calculating these forces, wind transverse, vertical and longitudinal, they are then combined. Okay, so we generally combined transverse with 50% of longitudinal, or maybe 50% longitudinal plus 50% vertical plus transverse full. Okay, because it's highly unlikely that all three of them will be acting simultaneously. Now moving on to thermal actions. Thermal actions are very critical for bridges where you have a restraint in the axial direction, and also it's important to check the actual expansion and contraction length of the bridge so that we can design the bearings. Okay, now thermal action has two components. We have uniform temperature and temperature difference. Okay, as shown in the figure here, which is taken from Eurocode 1 part 1.5. We have a uniform temperature which is equal temperature at the top and bottom fibers and all the fibers on the section, and then we have a non-linear temperature difference and a linear temperature difference. That's because different surfaces of the structure gets exposed to sunlight and humidity differently. Okay, so based on the type of the bridge, the code has specified some graphs and rules for calculating the temperature load on the structure. So we have these three types mentioned below. Then this is a graph which is for uniform temperature. So the maximum and minimum shade air temperature is given in the Eurocode in the national annex for different countries. Okay, so from that national annex we pick up the shade air temperature for that load, that particular area location, and from this graph we calculate the overall temperature, uniform temperature that we need to apply on the bridge. Okay, so based on a type 2, type 3, so x-axis is the shade air temperature. We just locate on the graph for different type of bridge and just calculate the uniform bridge temperature, and that uniform bridge temperature is then applied on the structure. Okay, so for example, if we get say 25 degrees as the uniform temperature loading, then that has to be applied as an element temperature in the software. Okay, so in order to apply the element temperature, we just select let's say the superstructure alone. Okay, and just go to loads, temperature, element temperature, and specify the value of the final temperature. Okay, so let's say 25 degrees and click select all and apply. Okay, for temperature difference we then move on to the next part, which is temperature difference. Okay, now Eurocode specifies different values of temperature at different heights on the cross section. So for composite steel girder types of bridges, there is a simplified approach where the temperature gradient is applied only on the concrete deck as shown here. Okay, but in case of sections which are say fully concrete, like concrete slab or concrete beams or box girder type of section which are deep, there is a nonlinear temperature gradient that is specified. Okay, so let me give you an example of such kind of application, how we actually specify that temperature gradient. Okay, now if we have to apply in the composite steel, it's very simple. We go to beam section temperature, select all the elements in the uncracked zone. We don't assume restraint moments in the cracked zone, so we don't apply temperature gradient in the uncracked zone. Okay, so in the in the cracked zone we don't apply any temperature gradient. So I'll just be selecting the box cutters over here, active, and just remove the temperature the cracked portion from here. Okay, so so from the top of the section, I'm going to say the section width is let's say 3 meters, which is the width of the slab, for calculating the strain value. Then material you can put as the material of concrete, E value and thermal coefficient. Height from the top is 0 and H2 let's say is 0.2 meters, and I mean H2 has to be taken from the code as specified over here. So H is the total thickness of the slab, so let's assume it's 0.2 meters, and then T1 and T2 is the temperature difference that we need to maintain. So let's say if it's 4 degrees and 4 degrees at the bottom, and we click add and apply. So that's how in a composite steel your average temperature gradient is applied. For a concrete section like the one which we had in our line beam model, I'm going to open that up. Okay, so you've got a wide deck here, but the actual beam element has been modeled as just the central spine has been modeled as an actual beam element. So the longitudinal direction temperature that I'm going to apply is for the entire deck that I will be selecting. Okay, so I'll select the spine beam in between. Okay, and just go to loads and temperature loads, element temperatures, sorry, beam section temperature. Okay, and then start applying from the top. Okay, so we have selected these elements, input the elasticity or take it from the material input directly. Width should be the total width of the deck, which is 24 meters, let's say, and height, let's say first temperature gradient will be from 0 to 0.2. Let's say it is a rise, temperature rise, so maybe 14 degrees to 7 degrees. I mean, I'm just taking arbitrary values, but we should be taking the values mentioned in this table. Okay, so 13 and 3, let's say. Okay, add. Then the next category is we move on and see the H2 category, H2 and delta T2. So we put another value, let's say from this time from 0.2 to 0.45. Okay, and this from 7 to 0. Okay, and add. Okay, and so on. We keep on adding all the temperature gradient values. So create a nonlinear temperature difference, and we run the analysis after that, and then look for stresses, internal stresses generated due to temperature difference. Okay, now we go to earth pressure. Okay, so earth pressure loads can be a little tricky. There can be different scenarios where you have the abutment and the soil acting as a backfill behind the abutment. either they can act as an active or passive pressure. Now, in case of such kind of loading, it can be um, a different scenario when we are combining it with other loads like live loads and SIDL. We need to have several cases where the backfill is acting as passive or active, and then apply the corresponding earth pressure coefficient to to reduce that problem. What the code has suggested, the published document 66941, which suggests a use of an equivalent K star value, which is equivalent earth pressure value, which can be applied on the abutments directly, uh, and then combine the results with other load cases. Okay, not only the load is not only the problem, the other problems include the actual compression springs that we, or the boundary condition that we input at the abutments. Okay, now in the software we do have methods to use nonlinear springs to define the abutment soil structure interaction, but that is a very tedious process, because for each nonlinear analysis it's difficult to combine the effects of other linear cases that, by using simple combinations. So in order to use springs, you have to create multiple models with different load combinations acting as one single load case. Okay, and that can be very complex, and to avoid that, we have an equivalent K star value which allows the user to ignore those soil springs and just apply the load, the soil pressure as a load directly behind the abutment. Okay, so when we are applying earth pressure load, we select the abutment which is normally modeled as plate elements. You can see here, modeled as plate elements, and we apply it as a hydrostatic pressure loads. Okay, I've just activated the plate elements and hydrostatic pressure loads. Reference value is top one, and then if there is any surcharge on the top, we can put that, or we can leave it blank. And gradient intensity will be the K star value multiplied by gamma, which is the dense unit weight of soil. So you have to put in these two, the product of these, and click apply, and you will have the soil pressure applied on the abutment itself, which looks like this. Okay, when you're applying soil pressure, make sure the direction of loading is global, is local Z, so it will be applied in the normal direction to the abutment. So you don't have to worry about if your abutment is inclined or in some other shape. Okay, so to calculate the K star value, we need the overall range of temperature expansion and contraction on the bridge. So that is calculated from T max minus T min, which again is calculated from the graph which of uniform temperature, which was covered in the previous slide. Okay, so we get the overall expansion or contraction in the bridge, which is then multiplied with the passive pressure coefficient and added to the earth pressure at rest to get the K star value. Okay, now move on to quickly to the actions during execution. During construction, we may have a different scenario totally, but we need to design for the structure for under construction separately from the one which is covered under service. Okay, so during construction, we may come across simple UDL or pressure loads like you have people moving around on the deck during construction, movable machinery, etc., which can be put in as a point load or UDL over a small area. Then there can be pre-stressing. So pre-stress we will be covering in subsequent webinars on our pre-stress bridges. Shrinkage and thermal actions, which cover the hydration effect. So this is something which I'm just quickly going to go back to the software and mention. So in order to make sure that we have the creep and shrinkage effects covered correctly, okay, the properties are defined for creep and shrinkage over here. Okay, so you've got Eurocode selected. You can use Eurocode or CEBFIP, which are similar to Eurocode, and put in the characteristic compressive strength here. Okay, notional size is very important. This is the size based on the exposed area of concrete. So 2 times area, exposed area upon perimeter need to be defined. Now what we define over here is just an initial um, member size, let's say 1 meter, but this has to be corrected and applied when we are defining the composite section for the slab. So for the slab, we just let's say open one of the composite section, and the notional size is mentioned here, which we need to correct. Okay, so we need to make sure that this is correctly calculated, although the software does calculate it automatically for the user defined section. Similarly, for other sections, concrete bridges, let's say for the pier, we can define it separately by using change property, apply, and it will automatically calculate the overall social size of the column pier. Apart from the creep and shrinkage function, the modulus of concrete also changes with time. So that is defined under compressive strength. Again, Eurocode can be selected and compressive strength of concrete has to be entered so that we get the correct time analysis. Okay, accidental actions like falling of precast segments, wind action, stability of steel girders during construction needs to be taken care of. One of the aspects where we use plate models is in this regard, where we have to calculate the stability of steel girders when the concrete has been poured on them. So I'm just going to open a simple model here. Which covers how we can analyze the buckling of steel when you have only got the steel girders in place and concrete has just been poured. Right, so this is the model where you have 4 steel girders placed side by side, and there are bracing 7 model. Concrete has been poured as a UDL, and we have performed the buckling analysis. So buckled mode shape looks like this. Again, this type of behavior, lateral buckling, which you can see the top flange buckling, can be observed only if you model the girders as plate elements. Okay. Okay, now moving on to traffic loads or live loads on road bridges. So as per Eurocode, we have 4 types of load models, model 1 to 4 for SLS and ULS checks, and some fatigue verification models. Apart from these vertical models, we have horizontal forces, braking, acceleration, and centrifugal forces, and footway loads and accidental loads, and also loads on abutments and walls. So in order to define these live loads, first step is to define the lanes. So since the Eurocode loads are applied on notional lanes, so we need to split up our deck into notional lanes and apply the position or location of those lanes on the bridge. Okay. Now in the software there are 3 ways of doing that. First is, if you have a line beam model, you can put an eccentricity to the center of the line beam and apply the line lane. Similarly, grillage model, you can have the live load distributed via the transverse beams, transverse grillage members, and then finally we have plate elements, which you can define the actual width of the lane and distribute the load as a distributed pressure load. Okay. So I'm going to quickly just cover up this part on how to define live loads. Now mostly since we have grillage models in design, so I'll just show an example of application of live load on a road bridge. Okay, so this is again a grillage model, and we have got this moving load feature here where we apply as a traffic line lane first. So I'm going to just open up some lanes. So lane 1, for example, we have lane width has been defined, and wheel spacing, because the axle load is split up into 2 wheel loads and placed on the transverse beams, which are then distributed to the longitudinal main girders. Okay, so an eccentricity has been used from the reference line to define these these traffic lanes. And if I display them, so let's say this is lane 1, you can see how they are placed. This is the reference line, and from there the eccentricity has been taken and the loads have been defined. Okay, then after that the next step is defining the vehicles. So first type of vehicle is the load model 1. Load model 1 has axle loads as well as UDL. It's got a tandem load, 2 axles with and it's applied throughout the bridge in all 3 lanes, and then you have a remaining area. Okay, so in the vehicles you have load model 1. Okay, adjustment factors are used for each lane based on the importance of the lane, motion lane 1 or 2. So this positioning of the vehicles is done by the software automatically based on an inference line analysis. Then apart from this load model 1, which is used to model normal traffic, we have load model 2, which is used for local verification of elements only, for short structural members, because it uses a very heavy axle load of 400 kilonewtons. Then there is load model 3, which is used for long axle combinations like truck loads and special vehicles which can straddle between 2 lanes are also there. These loads are then multiplied with dynamic application factor for speeds greater than 70 kph. Then load model 4 is for crowded situation, on specially used on footbridges and also on highway bridges which can expect crowded condition. Yep. So here we have got all the different types of loads defined. You've got load model 3, which is SV100 or any other cases. You can just click, you can create, the software gives us a feature to create our own special vehicle also, which you can create here. This is used in the case of assessments mostly as compared to design. Okay, horizontal loads. Horizontal forces are defined as a static load, since we can't automatically use influence line analysis for horizontal force in the software. We generally define the braking and acceleration forces calculated as per this equation and apply it in the software at the bearing locations which are expected to attract the braking or acceleration forces. So these are applied as point loads in the longitudinal and transverse direction if it's a curved bridge. Centrifugal forces again are applied on the entire length of the bridge for simply supported bridges in the transverse direction. So again you use element beam loads for this type of load generation. There is a feature by which you can generate centrifugal forces automatically in the software by using the tracer, moving load tracer function, okay, and convert the vertical loads into centrifugal forces at the exact location of the vertical loads. Okay, now once we have put these vehicles on different lanes, we need to combine the traffic loads as per the combinations given in UK National Annex. So the first type of combination is group 1A, which is for normal traffic only. We have load model 1 on all the lanes. Okay, so the way we define it is in load cases, we select the lanes, lane 1, 2, footway lanes. So load model 1 is combined with footway, 60% of footway loading, and then the remaining area is also applied with remaining area, the load corresponding to remaining area. Then group 1B is just load model 2, which is used for local member checks, heavy load. Group 2 is a frequent combination of load model 1 with braking and acceleration. Okay, so as shown in the figure here, we apply the vertical live load, plus we combine the vertical live load results with static loads, which we, as I mentioned, we applied as point loads at the bearing locations. Then group 3, which is just the footway loading, applied on the footway. Group 4 is just the crowd loading, and then finally group 5, which is generally the governing combination because it's got the heaviest axle loads, the special vehicle plus the load model 1. Okay, now the special vehicle and load model 1 has placed in such a way that we maintain a distance of 5 meters on between the axle load and axle of load model 1 and axle of load model 3. This particular placement is again taken care of by the influence line analysis of the software, and it actually gives you the position of the vehicles corresponding to these diagrams. Then comes fatigue load models. Fatigue load models, mostly fatigue load model 3 is commonly used, which is shown in the figure here, and only one lane has to be loaded with fatigue load model 3, and if you are doing a ULS check, we should have only this particular load case in our combination for checking the stresses for fatigue. Then accidental traffic loads, sometimes there can be vehicle collision with curves. The Eurocode has suggested few loads that can be applied in transverse, longitudinal, and vertical direction. So they are applied as point loads simply at the locations where the collisions are expected, just say near the parapets or curves, etc. Then we move on to traffic loads on railway bridges. For railway bridges, we have got different load models for passenger heavy freight, and also a special load model for high speed trains. So now let's look at few of the examples here. The process of applying the traffic loads is similar to what we saw in highway live load. We just define the lanes first. In case of our train loads, the lanes definition is very simple. We just define two tracks and just define the distance between the wheels of the train, and the wheel spacing will be equal to the spacing of the rails. Basically, lane width doesn't have a real meaning here. We can put some value which is equal to wheel spacing. Okay, for vehicles, we define the vehicles again. Standard vehicle, we got rail traffic load model 71 and etc., and then combine them just like we did for highway live loads in the moving load cases. The most important thing, however, is the railway dynamic factor, which depends on different elements. Okay, so our longitudinal girder will have a different determinant length for calculating the dynamic load factor, and so is the cross girder, which has a different length. Okay, so when you apply the railway dynamic factor, the software comes up with a feature where you can individually select an element and assign dynamic factor based on the code. So there are some functions given in the code for different types of tracks and different types of bridges. These are used to calculate the dynamic load factor and apply it on the structure. Again, centrifugal forces, braking and traction are applied at the top of the rails longitudinally, braking and traction applied longitudinally along the loaded length as a UDL, and similarly centrifugal force is applied in transverse direction as element beam load. We'll not be going into details of track bridge interaction here, but you can actually do a very detailed rail track structure interaction due to temperature plus braking effects. Okay, so we'll be covering it in some other webinar. Dynamic analysis of high speed trains. So in this type of structures where you have high speed trains going on, we do a time history analysis of the train loads. So each train load is modeled as nodal loads and applied at a different time interval on the structure. Okay, and then it's the whole time history analysis is run. It gives us a plot, acceleration versus time plot like this, and we just compare the peak acceleration to check whether it is in the comfort zone or not. Similar to the dynamic analysis of heavy rail loads, we also have dynamic analysis of footbridges. Now this is more of a serviceability check where we just are focused on the acceleration of the peak acceleration of the footbridge under human induced vibrations. Okay, it's an interesting method of analysis where we check the first of all the natural vibration of the footbridge, and if it's within a particular value of frequency like shown here, we run the analysis in more detailed manner for dynamic loads. Okay, so the code has defined few functions that need to be considered for dynamic analysis. Again, we have a separate webinar schedule for footbridge action, which you can read or go through in full detail for those type of functions that are defined. Then the result that we obtain is this such kind of acceleration versus time plot, where we can take out the peak acceleration measured with the code limit. Okay, now move on to accidental actions. In accidental actions, we have impact or collision loads. As shown in the figure, for bridge pier, ship collisions on the bridge pier, or vehicle collision, the exposed area is used to calculate the force, which is then applied, equivalent static force, which is then applied on the bridge component as a point load. Then there is a special case for accidental action where you can have a loss of tension component. A lot of cable stayed bridges and a lot of cable structures are coming up in the UK and also other parts of the world, and this is a very important check that we need to make sure, not just in service but also in construction. So I'll just take an example of a simple cable bridge. Okay, so this is an extra dose bridge, so we can check for the hanger loss, cable loss scenario in one of the construction stages. So let's say this is the scenario. If we remove one particular cable, what we do in this check is simple, calculate the forces in the cables first in the normal state. So we have got some X force here, and then when we remove the cable, we apply the same force in the backward direction on these two nodes, and with a multiplication factor of 1.5. This is given in Eurocode 3.1.11, and after applying this force, we then perform another analysis to calculate the overall effects of this force on the other components of the bridge, and that gives us the accidental loss effect. So this is used for both, this is used for the QLS check. Then move on to the other subject of imperfections. Imperfections can come as a result of both change in the geometry during construction and also due to residual stresses. Now both of these effects are covered in the code in the clause 532 Eurocode 3.1.1. This is very common in steel compression members, especially in the case of like arch bridges, where we can put a global imperfection in the model using the buckled shape. So I'm just taking a quick example of an arch bridge. Okay, so this is an example of an arch bridge, tied arch bridge, and we've got the top bracings here. So I'll just focus on them. Now to put imperfections in the model, we need to first look at the buckled shape of the structure. So we've got a buckling analysis set up with the ULS combination dead load plus live load, and we'll be looking at the buckled mode shape of mode 1, which typically for an arch looks like this. Okay, and using this mode shape, we update this model with imperfection. We put a maximum imperfection value, which is taken from this the code, the same code we mentioned before. So put, let's say, 0.1 meter as the maximum value of imperfection. Now update the structure based on that shape. Okay, so you've got, if you see, there is a slight shift of the top arch here. which is shifted by 0.1 meters in the lateral direction. Okay, and then we run the nonlinear analysis on this deformed shape and calculate the moments and other values. Okay, now to avoid this situation, the structures which are braced with a lateral bracing system like the ones which we saw, to avoid this entire analysis, we can go through an alternate method where we calculate the forces, equivalent forces based on the clause given here, and apply it at the bracing points location. So this will give us the moments due to second order effects that we obtain normally from more complex method like buckling analysis. Okay, so this method can also be used for calculating the effects due to imperfections. Okay, so that brings us to the last topic, which is load combinations. It's very crucial in Eurocodes to apply the correct combinations and look at the design the sections as per these combinations. So there are two parts of any load combination in Eurocode. First is there is a psi factor which is given for different loads like traffic, wind and thermal actions. These are given in the UK National Annex for Eurocode 0. So these psi factors are then multiplied with the gamma factors which are given for different actions. So based on whether the load is leading or accompanying, your psi factor varies, and then we multiply the permanent action with gamma plus the variable leading action with again gamma q, and the variable accompanying action with psi times gamma q. Okay, and that's how we generate different combinations for ULS and SLS checks. Okay. There are two types of combinations mostly, if I say one is for structural strength and one is for stability or equilibrium. So that brings us to the end of the presentation today. For any types of questions, please write to the Midas team, and thank you for watching.